Hi and welcome to lecture 3 of module 7 where we are considering ordinary differential equations initial value problem. So far in the first two lectures we have looked at what we mean by the numerical solution of ordinary differential equations. We considered Eulers methods, Eulers implicit and Eulers explicit method, and then in the previous lecture, lecture 2, we moved on to RK2 method. Specifically we talked about the second order RK method. Okay. So let me just go over some of the results of the RK2 method that we derived in the previous lecture. Okay. So the RK2 method in we are going to obtain our yi plus 1 is going to be equal to yi plus h multiplied by some slope s computed explicitly based on the values of yi and ti. That means we are not going to use the value of yi plus 1 in order to compute this slope s. For RK2 we chose the slope s as a weighted sum of the slopes computed at two specific points within the overall interval. So s we wrote that as equal to w1 k1 plus w2 k2, okay, where k1 was equal to function f computed at yi comma ti, and k2 was f computed at yi plus some value q multiplied by h multiplied by k1 comma ti plus some value p multiplied by h. Okay. So that was our k1 and k2, and the conditions that we derived okay, we derived certain set of conditions for RK2 method, and those conditions gave us the order of accuracy as h to the power 3, and those conditions were w1 plus w2 equal to 1, w2 times p equal to 1 by 2, and w2 times q equal to also 1 by 2. And based on these two equations we said that p equal to q is one equation, w1 plus w2 equal to 1 is the other equation, and w2 p equal to half can be the third equation. So p is equal to q is one of the things that we obtain is in the RK2 method, second order RK2 method. And the geometric interpretation of the second order RK2 method is when you are going to plot y against t, and we have any arbitrary curve of this sort, and let this be ti and let this be ti plus 1, which with the difference between the two being equal to the step size h. At that time k1 is nothing but the slope computed at this particular location, and that slope is represented by this particular yellow line, and that is going to be our k1. Okay. And we take certain point not at an arbitrary location, but maybe this particular line does not exactly represent the slope very well. Perhaps I will just redraw that line. Okay. So now we have this particular guy as k1, and then what we said is now we select one point, and this particular condition tells us that this particular point is going to be selected somewhere along this line, not at an arbitrary location in this rectangle, but somewhere around that line, perhaps over here, and then we compute the slope at that particular x at that particular point, and that slope, let us say, is this guy, and that is going to be our K2, okay. And thus the value of S that we are going to consider is going to be a weighted average of K1 and K2, and that value might look somewhat like this, and this is going to be the point yi plus 1 that we will get, and this the slope of this purple line is going to be nothing but S, okay. So this is the geometric interpretation of the RK2 method. So the yellow line that I have shown over here is the geometric interpretation of the Eulers method. The purple line that I have shown over here is the geometric interpretation of RK2 method. The two specific RK2 methods that are of greater interest to engineers, one is the midpoint method. In midpoint method we had chosen our P equal to half, so our Q also was equal to half, W2 was equal to 1 and W1 was equal to 0. So P equal to Q equal to half, W2 equal to 1, W1 equal to 0 was the midpoint method, and the other method was Yoons method, for which we had obtained P equal to Q equal to 1 and W1 equal to W2 equal to half, okay. This is what we had obtained for Yoons method. In the previous lecture, what I had mentioned but not really expounded on it was that in some ways the idea behind Yoons method is kind of collinear or similar to the idea behind the trapezoidal method, and let us see why I made that particular statement. So let us consider the case where this particular function f of yi comma ti was not a function of yi explicitly, but it was only a function of ti. If that is the case, okay, if f is just going to be a function of ti, then k1 is just going to be equal to f of ti. For Yoons method we are talking about, k2 is going to be nothing but f of ti plus ph, and p for Yoons method is equal to 1, and so that is going to be ti plus h, okay. So f is going to be ti plus h, which is nothing but f of ti plus 1, okay. So our S is going to be half multiplied by k1 plus half multiplied by k2, which is f of ti which is equal to f of ti plus f of ti plus 1 divided by 2, okay. So now if we had to solve dy by dt equal to f of t using Yoons method, okay, the expression that we are going to get from Yoons method is yi plus 1 is going to be equal to yi plus h multiplied by s, and h multiplied by s is nothing but h by 2 multiplied by f of ti plus f of ti plus 1, and this particular term for us is reminiscent of nothing but the trapezoidal rule, right. Trapezoidal rule was for the trapezoidal rule we obtained, the trapezoidal rule we had obtained as follows: dy is going to be f of t dt and then we integrate this from Ti to Ti plus 1, and this is going to go from Yi to Yi plus 1, and the trapezoidal rule would give us Yi plus 1 minus Yi is approximately equal to h by 2 multiplied by f of Ti plus 1 plus f of Ti, okay, which is same as the expression that we get from the Yoons rule. Okay. So, for this reason I had made a statement that Yoons method reminds us of trapezoidal rule. Okay. And recall from the what we did in module 6 is trapezoidal rule also gave us order of h cubed accuracy. Okay. It is actually not really the Yoons method reminds us of trapezoidal rule. Originally the Yoons method was developed as a predictor corrector method, and we are going to talk about that later on in this particular lecture in a few minutes from now, what the predictor corrector form of the Yoons method. But to go over what we have is in Yoons method, what we do is we find the slope at this point, the slope at the projected point, and the true slope S that we are going to use for moving forward with the ODE solving is going to be just just an average of those two slopes. Okay, that is about the Yoons method. Before going on to the predictor character idea of Yoons method, let us very quickly go over the Eulers method and derive the expression for accuracy of Eulers method. So Yi plus 1 is, if we do a Taylor series expansion of for Yi plus 1, that is going to be equal to Yi plus h multiplied by f of Yi comma Ti plus h square by 2 factorial multiplied by plus dot dot dot. We actually have d square y by dt square, and dy by dt is nothing but f. This is the derivation that we had actually done in the previous lecture. So I am just using shorthand over here. Okay. So now if we drop these terms, we will get accuracy of order of h squared, and our Yi plus 1 is going to be approximately equal to Yi plus h of f Yi comma Ti. Okay. And we have dropped these terms, so the accuracy of the Eulers explicit method is of the order of h squared. Okay. So the Eulers explicit method is h squared accurate, whereas the RK2 method is h cubed accurate, that we had derived in the previous lecture. Like trapezoidal rule, our Yoons method also is h cubed accurate. So to summarize the accuracies, okay, Eulers method that we just derived is accurate to the order of h squared. RK2 that we derived in the previous lecture is accurate to the order of h cubed. The best RK3 method is accurate to the order of h to the power 4. RK4 method, the best one, is accurate to the order of h to the power 5, and now this is where the fun starts. is RK5 method is also accurate to the order 5. Okay, h squared, h cubed, h to the power 4, h to the power 5, and we go for a more number of terms in the Runge-Kutta method, but the order of accuracy does not increase. So there is not a big jump in accuracy that we get by going to more computationally complex RK5 method. As a result of this particular observation, RK4 method is usually the method of choice for solving ODEs. Okay. In fact, in various packages such as MATLAB and Mathematica and so on, as well as a lot of codes that you will get for download at various different sources for initial value problem of non-stiff nature, and I will come to explain what the term stiffness and non-stiffness means perhaps 2 lectures from now. But for a typical ODE IVP, you will find that the RK4 method is perhaps the most popular method that is used, and RK4 is has an accuracy of the order h to the power 5. So it's since it's an RK4 or a 4th order RK method, our S is going to be written as okay, W1 K1 plus W2 K2 plus W3 K3 plus W4 K4, okay, where K1 is going to be written as f of yi comma ti, K2 as we had before is going to be written as f of yi plus q, and now we will put subscripts for q. We will write this as q11 h multiplied by K1 comma ti plus p1 multiplied by h. Okay, our K3 is going to be f of yi plus q21 h K1 plus q22 h K2 comma ti plus p2h, and K4 is going to be f of yi plus q31 h K1 plus q32 h K2 plus q33 h K3 P3h. Okay. So what we do is we compute slope at 4 different locations within Ti and Ti plus 1. Okay. So if we go back to this particular figure that we have drawn, we will compute K1 at this particular point, then we choose a point in this rectangle, an arbitrary point in this rectangle, find the slope K2. Based on the slope K1 and based on the slope K2, we find out another slope K3 at another arbitrary point, and that arbitrary point will lie in this particular rectangle. Okay. So the third point will lie in that particular rectangle, and find the slope at that particular point K3. Okay. And another point, 4th point, will also lie in that in another rectangle so constructed, and that slope will be K4, and the final S that we are going to use in order to compute the term yi plus 1 is going to be a weighted sum of K1, K2, K3 and K4. Okay. The most typical RK4 method that's often used has W1 equal to 1 by 6, W2 and W3 equal to 1 third and W4 equal to 1 by 6 again. So common slash typical common or typical RK4 method has K1 plus 2K2 plus 2K3 plus K4. K1 of course is f of yi comma ti. K2, just like the midpoint method, K2 is going to be f computed at yi plus h K1 by 2 ti plus h by 2. Okay. K3 is f computed at yi plus h K2 by 2 comma ti plus h by 2. Okay. And K4 is going to be f computed at yi plus h K3 and ti plus h. Okay. So this is the most typical RK4 method. What RK4 method actually will do, okay, is I am not going to draw the true curve over here. Okay, this is ti, this is ti plus 1, and let us say this is our yi. Okay. So our first slope is nothing but slope of that curve. Let us say that curve is somewhat like this. Then our first K1 is going to be just f of yi comma ti. Okay. So let us say K1 is actually shown by this particular white line. Okay. So now K2 is going to lie, because our Q11 and P1 are both equal, our K2 is actually going to lie on this particular line itself, and K2 is lying actually on the midpoint. So K2 is computed actually at the midpoint. So K2 is actually computed at the central point over here. Okay. And K2 is going to give us a slope at this particular central point. So let us say K2 is given by this yellow line. So what we do is then we go back and then we project that yellow line over here, and we will get that particular yellow line looking somewhat like this. K3 is going to be a point computed again at the midpoint, but this midpoint is now computed using the slope K2. So the K3 is computed, okay, on the same vertical line over here, but at this particular location, and that is going to be the value K3, and let us say for argument's sake K3 looks somewhat like this. So we go back to this particular point and then project K3 again. Okay, and K4 is then computed at the final point, and that I am going to show with a pink color. So K4 is going to be computed at this particular point, and let us say that the slope at that point is over here, and so that red line is going to be the fourth slope. Okay. So the white line represents the slope K1, yellow line represents the slope K2, the purple line represents the slope K3, and the red line represents the slope K4. Okay. And the final S that we are going to use in order to compute yi plus 1 is going to be K1 plus 2 times K2 plus 2 times K3 plus K4, the whole thing divided by 6. Okay. So that is the geometric interpretation of the simplest of RK4 methods. Okay. In one of the summary lectures, I will go over the various different types of RK4 methods that people have actually come up with over the last 60-70 years, So now what I will do is I will go on to Microsoft Excel and solve the specific problem of the PFR. The PFR problem, the design equation that we had solved, we had obtained a design equation based on the overall equation dC by F multiplied by dC by dV, where F is the flow rate, volumetric flow rate, that is going to be minus Kc to the power 1.25. Okay. So that was the overall expression, and then we converted that through straightforward techniques. We had converted that to get give ourselves the design equation V equal to F times Ca0, which we had called Fa0, multiplied by integral from 0 to x dx divided by minus r of x. Okay, where minus r of x was nothing but k multiplied by 1 minus x to the power 1.25. Okay, and then we had plotted f Ca0 divided by k multiplied by 1 minus x to the power 1.25. we plotted that against x, and the area under that curve that we calculated was equal to V. Okay. So instead of solving this particular problem, we are actually going to be interested in solving this this particular problem. And if you recall, in the previous previous module, the value of f Ca0 divided by k, we had taken that equal to 2. So and Ca0 was equal to 1. So what we had okay. So for these conditions, we had tried to solve this PFR problem using the integration method, using the design equation of the PFR. We can rearrange this and we can get an analytical solution. Okay, and k by f for Ca0 equal to 1, k by f is nothing but 1 by 2. So this we can write as c to the power 1.25 divided by 2, and we can just rearrange that and we can write dc, and I forgot the minus sign over there, dc, negative of dc divided by c to the power 1.25 is going to be equal to dv by 2. And then when we are going to integrate this, we are going to get c to the power minus 0.25 divided by 0.25. Okay, there will be a minus sign over here and there is a minus sign over here, that is going to be equal to v by 2, and c going from Ca0 to the value Ca. Okay. And then if we rearrange this entire thing, we will get Ca to the power minus 0.25 minus Ca0 to the power minus 0.25 is going to be equal to 0.25 multiplied by V by 2, that is going to be V by 8, okay, plus Ca0 to the power minus 0.25, okay, and so Ca to the power minus 0.25 is going to be equal to this term, and then we will divide by minus 0.25 in the exponent over there, and we will get this as Ca equal to Ca0 to the power minus 0.25 plus V by 8, where V is the volume of the PFR, whole raised to the power of minus 4. Okay. So that is the analytical solution, and this is the problem that we will try to solve numerically, and using the Eulers method, using the Runge-Kutta second order method, and then we will compare the results that we are obtained from the two methods. Okay. So, now we will go on to Microsoft Excel and we will try to solve this particular problem. So, now the problem that we are going to solve is dc by dv was equal to minus c to the power 1.25 divided by 2. Okay. That is the expression that we have just derived a few minutes ago on the board. Okay. So, I will write that down. dc divided by dv is going to be equal to minus c to the power 1.25 divided by 2. Okay, I'll just write that down again. By dc by dv equal to minus c to the power 1.25 divided by 2. Okay, and I will just format cells and make that superscript. Okay. So, this is the problem that we are trying to solve with C0 equal to 1.0. Okay. So, that is the problem that we are trying to solve, and let us get the true solution. Okay. So, we will have V and the corresponding C concentration, and as we had obtained earlier, the true solution is actually going to be equal to the concentration Ca0 to the power minus 0.25. Ca0 is 1, so 1 to the power anything is also going to be equal to 1, plus volume multiplied volume divided by 8. The volume is given over here, this guy divided by 8, the whole raised to the power of minus 4. Okay. So, that was the value that we had obtained. So, let us look at the volume of the reactor going from 0, 1, 2, let us say up to 10, and let us find out the concentration that we get from this particular figure. Okay. Now, let us try to see what values we had derived in the lecture on integration. At that particular case, what we had said is we need to find out the volume that gives the conversion of 90%. 90% conversion means that the exit concentration C that we get from the reactor is going to be equal to 0.10. So, the solution, the actual solution is going to lie close to 6. So, the volume is going to be close to 6. So, what I will do is between 6 and 6. Say 6.1, 6.2 and so on, I will just plot a few more values. Okay, and 6.3 as well, and let us see what values we get over here. Okay. So, between 6.2 and 6.25 the value has gone below 1. So, perhaps our solution is going to be between, not perhaps, definitely our solution is going to be between 6.2 and 6.25. So, let us try to actually get that solution also. So, 6.2, 6.21, 6.22, 6.23, and so our solution is somewhere between 6.22 and 6.23. Okay, and let us go and look at what our Newton Cotes integration formula had given us as the volume that will give us 90% conversion, and the Newton-Cotes formulae, the 1/3 rule, the results that we got was 6.2262. that was the volume of the reactor that gave us a 90% conversion, and the analytical solution gives us the value as 6.22 something. Okay, we can just go a little bit further and we can get the actual result, and we will be able to find that the values indeed that we obtained using integration were the same as the values that we will obtain using the true solution, the true analytical solution. Okay. So this we can use as one more check to check our integration that we did in our previous lecture. Okay. So now let us use Euler's method. Okay, Euler's explicit method with certain value of h. Let's choose the value of. Okay, I'll just insert. Okay, so let's choose the value of h equal to 1 and see what the Euler's method gives us. Okay, and one of the things that that happens with Euler's method is that Euler's method is not always Euler's explicit method is not always stable. What that means we will talk about soon. Okay, so Ci I'll write over here. So initial Ci is going to be equal to 1. Okay, the Vi is nothing but the independent variable. The value of Ci at Vi equal to 0 was equal to 1. Okay, I'll just move this over here. We usually put our independent variable in the first column. So Vi equal to 0, our Ci is equal to 1. Let's compute our f of C comma V. Okay, and our function f is dc by dv equal to minus c to the power 1.25 divided by 2. So it is going to be equal to, okay, I'll increase the font size. So this is going to be equal to minus c to the power 1.25 the whole thing divided by 2. Okay, that is going to be our value of f. Okay, so the value of f is going to be minus 0.5. Okay, now this guy is going to be equal to previous guy plus h. Okay, and I'll put dollar signs over here. Okay, and remember the Euler's explicit method is yi plus 1 equal to yi plus fi. Okay, that was the expression, sorry, yi plus h multiplied by fi. Okay, so yi plus 1 equal to yi plus h multiplied by fi. Now we will go and put dollar signs in front of h, so that when we drag and drop this we do not have to go and change our h. Okay, and now we will just drag it down up to 10. Okay, and then drag this f value below. Okay, and we will just go ahead and check what we see with this. So f2 is going to be sorry, C2 is going to be nothing but C1 plus h multiplied by f1. Okay, that is what we get over here. Now we will check the value of f of Ci comma Vi. Of course, f of Ci comma Vi again we get as negative Ci to the power 1.25 divided by 2. Okay, so this is what we get. Okay, now if we compare the Euler's explicit method, the errors that we get with the true solution, we see that there are some amount of errors between the true solution and the Euler's explicit method. So, we will just plot the errors over here. So, errors are going to be equal to the absolute value of the difference between Ci true minus Ci that is obtained from the numerical solution divided by the Ci true. Okay. So, that is the error of course right in the beginning the error is 0, and as we proceed further the error is, so this is a relative error, and the relative error is actually as high as, so it starts with 20%, goes to approximately 30%, and eventually we get error as high as 40% using the Euler's explicit method if we choose h equal to 1. Okay. So, this is what we get with Euler's explicit method for h equal to 1. Okay. Now, we will again use Euler's explicit method for with h equal to 0.5. Okay. So, what we will do is h will redo this for h equal to 0.5, and this is going to be this guy, and I will put the dollar signs over there. Okay. Our f is again correct. Now, let us get our Ci plus 1 that we have. Ci plus 1 over here is going to be nothing but equal to Ci plus h multiplied by Fi, and we will go back and put dollar signs in front of h, so that we get this. We just drag and drop this over here, and we will do this over here as well. Okay. Drop this over there, and we will just copy this down . Okay, and 0.5, so that we are able to compute it for the same set of values. Okay, and these are the errors that we get with h equal to 0.5. Okay, now if we compare the errors that we are getting for the Euler's method using h equal to 1, I will just copy this and put them over here. Okay. So, at the volume equal to 1, the error using the h equal to 0.5 in Euler's explicit method is almost 8%, whereas it was almost 20% using h equal to 1. For this guy the error is again half of what we obtained using h equal to 1, so on and so forth. Okay. So, this is what we see for h equal to 4, again the error is 38%, whereas error using h equal to 0.5 at volume equal to 4 is approximately 18%. So, error is approximately half using h equal to half compared to h equal to 1, and what we will do is we will just carry it out until 10. And we will do the same thing over here as well. Okay, and these are the errors that we get. Okay, and the Euler's explicit method we will repeat it once again for h equal to 0.25, and then we will do the plots. okay, and the volume is 0. At volume of 0 we will get C equal to this. Our F, we will write this as, again we can just copy and paste it, that is not going to be a problem. We will write H equal to 0.25. Okay, and next value of V is going to be Vi plus 1 is going to be Vi plus H, and then we will again put, as we have been doing always, we will put dollar signs over there, so that when we drag and drop we do not get any problems, and then we will go right up to volume of the reactor equal to 10. Okay, and the concentration C is going to be equal to, so Ci plus 1 equals Ci plus H, and for H we will put dollars because H is not changing, multiplied by Fi. Okay, so Ci plus 1 equal to Ci plus H multiplied by Fi. Okay, and then we will just double click this and we will double click this so that our solution is now obtained. And now we will plot the true solution as well. Okay, and the true solution I will just double click this and this will give us the true solution, and then I will compute the error as well. Okay, yes, and we have the computation at error over here, and error is the absolute value of true solution minus the numerical solution divided by the true solution. Okay, and I will just double click this and we now have the error using H equal to 0.25. Okay. So, now what I will do is create a plot of how the error changes with volume for the 3 different H values. So, I will choose this as our x axis, I will choose this error as the y axis. I will click on insert, and then we want a scatter plot, and this we want it connected by smooth lines. Okay, so this is going to be our scatter plot. I will increase the font sizes now. Okay, so what we are plotting over here is how the error changes with the volume for the PFR. Okay, and then I will add another set of data. The x values, these are the x values. The y values are going to be these errors over here, and okay. So, the second series is Eulers method using H equal to 0.5, and we will add one more series with errors using 0.25. Okay. So, this blue line represents the error using the Eulers explicit method with h equal to 1. The red line indicates Euler's explicit method with h equal to 0.5 and the green line indicates Euler's explicit method with h equal to 0.25. One of the things that you see is what is known as the propagation of errors. As we go farther and farther away from y0, we see that there is that the overall truncation error increases. How the error changes from one point to another point is what is known as the local truncation error, and how the error changes overall throughout the overall solution is known as the global truncation error. Okay. At each point we are trying to find out the difference between the true value of concentration and the numerical value of concentration. So, what we have plotted over here is not the local truncation error, but what we have actually plotted is the global truncation error. So, in case of Euler's method, although the local truncation error scales as h squared, the global truncation error scales as h. So, what we see is when we are going to half the h value, the overall errors are also going to reduce by the same factor. So, when we go from h equal to 1 to h equal to 0.5, the overall errors have halved. When we go from h equal to 0.5 to h equal to 0.25, again the errors have halved. If we go from 0.25 to 0.125, again the errors are going to be halved even further. Keep in mind that when I say half, it is not exactly half, it is approximately half, because in the derivation using basically using our mean value theorem, we do get f of f at t zeta comma y zeta, where zeta is a point which lies arbitrarily between ti and ti plus 1 and yi and yi plus 1. This particular point is not known a priori, so we cannot exactly say that the errors are going to reduce exactly by half, but approximately the errors are going to reduce by half, and that is what we have consistently seen when we compare this blue line, which was for h equal to 1, with this red line for h equal to 0.5, with this green line for h equal to 0.25. Okay. So, this is now where we come to end of this particular lecture of this module. So, what I am going to cover in the next lecture is I will go over these results for Euler's explicit method once over again, and show you how this overall errors are changing when we change our h value for the Euler's explicit method. Then I will take on the midpoint method and solve using the midpoint method, also solve using the Yoons method. I will solve the same problem of ODE solving. Next we will go on to the predictor corrector form of Yoons method. Okay, thanks and see you in lecture 4 of this module.